Please resume.
Okay, okay, sure. So we talked about word embeddings and especially the most recent techniques for word embeddings, these transformer-based BERT models and all. So now we will look at how to make, convert them into multilingual word embeddings from a single language one, and how that helps into cross-lingual zero-shot transfer. So like we said, right, pre-training requires a huge amounts of unlabeled data in a language. So the more the amount of data, the better the language model or the embeddings that are learned. And fine-tuning requires a substantial amount of label data. It's not huge, but still a substantial amount of label data in in a particular language. So typically 100,000 labeled examples. So and we all know that label data is more difficult to collect, more expensive to collect. So how nice it would have been, right, if we could actually pre-train with a large number of languages with fewer amounts of data, and we could fine tune with one language and it could work across all languages. And this is the idea of cross-lingual word embeddings, and it's not very new, meaning it's not like there were cross-lingual word embedding models before even multilingual BERT. So the initial ideas were as follows. Imagine I have two languages, L1 and L2, and I have separately learned two embedding models for them. So let's say two word-to-vec models, one for L1 and one for L2. Now they are in different spaces, right? So the word embeddings of L1 and word embeddings of L2 are not directly comparable. What people thought is, can we now use something like a dictionary or a parallel data, little bit of parallel data between L1 and L2 to map the embeddings into the same space. So let's say I have learned separately the embedding for cat, I have learned separately for the embedding for billy, and similarly dog and kutta. Now I know that dog is same as kutta and cat is same as billy. So can I use these mappings to actually learn a transformation that transforms all the Hindi embeddings to a space which is same as the English embeddings? And my constraint there for transformation is cat should be as close to billy as possible and dog should be as close to kutta as possible in the embedded space after transformation. So this is the whole idea of this cross-lingual word embeddings. So essentially some sort of a zero shot is happening, or a transfer is happening. Now there are many such methods, and I will share the slides. So there are surveys about it, and you could go through them, but these are a little dated, so to say. uh, One interesting thing I can just mention is we showed in some of our own studies that you could actually use code mixed data to kind of learn cross-lingual word embeddings. So code mixing is when people use more than one language in a same sentence. So let's say Hinglish. I was thinking agar udhar jata to it would have been very nice. So this is a English sentence where I have mixed both Hindi and English. Now, if you have lots of examples of a corpus of such English sentences, you could automatically learn cross-lingual word embeddings between English and Hindi. So as an aside. So the first, massively multilingual word embedding. So cross-lingual is typically between a couple of languages, right? Two languages, L1 and L2. So massively multilingual embedding, the first idea was, proposed by Google in 2016. It's called this Google, zero shot machine translation by Google's multilingual neural network. Idea was as follows. So you train a neural net, which has an embedding layer in between and everything, um, for translating between, let's say, English and Korean, and Korean and English, and similarly English and Japanese and English. So those were the data sets you have: English to Japanese and Korean to English. But you did not have any data between Japanese and Korean, right? But suddenly, once you train this single model with all these languages, it starts automatically working between Japanese and Korean. So this was the first example where you could have zero shot transfer or cross-lingual transfer without absolutely any data. So you didn't have any parallel data in Korean and Japanese, and it worked reasonably well. Further, in the same Google paper, right, they looked at how the embedded space looked like. And what they found is, I mean, here the example has 3 languages, but actually in the paper they probably did, I mean, a large number of languages. I forgot the actual number, maybe 20 or 30 languages. And what they showed is something like this, that suppose you look at a particular sentence. The sentence is the stratosphere extends from about 10 kilometer to about 50 kilometer in altitude. And its translation in Korean, its translation in Japanese, and so on. And similarly another sentence and its translations, and what they saw is those translations get clustered in embedding space. So in sense, what's happening is the translator, this model in between, is learning a multilingual embedded space where no matter what the language is, it's getting embedded into the same space. So similar words, similar meanings gets translated to the same space. So it almost looks like a universal semantics. This model is learning a language independent universal semantics. So any language you put in there, it will start working. Of course you have to have some training data to put in there. Yeah. So this was the initial idea in 2016. In 2017 transformers came, in 2018 BERT came, and in 2019 people thought, okay, in the Google's model, right, we still required parallel data between English and Japanese and English and Korean. Now parallel data is expensive. What if I did the same unsupervised training with only, let's say, masked language model, but I used the same model with all languages? So I put in English, Hindi, French, Swahili, corpus, I mean, data, everything together. I mixed them, like one English sentence, one Hindi, then after that one French, maybe a couple of Swahili sentences, all in the same batch or mini batch. And then I used an MLM training like I would have done only for a single language. Now, there is no reason to imagine that the words will be mapped to the same space. Hindi words might form a cluster, English words might form a cluster separately in the space, right? So there is no reason, because there is no mapping between Hindi and English or Hindi and French and so on. No data to learn such mappings. But what they showed, and I told you already, that it works. It simply works that you train a task specific fine tuning layer for, let's say, English now, and it automatically starts working for Hindi, French, Swahili, and all the other languages. So this was what was this massively multilingual language models paper that came in 2019, and eventually people tried to make it further better, push in more languages. So you have XLM Roberta, you have Microsoft has a similar model called Turing, and everybody is now thinking about moving. I mean, everybody in the sense, all big companies like Microsoft, Google, Facebook are talking about moving to these models to serve a very large number of languages. And it's possible now because you no longer need now labeled data across all these languages. So you need labeled data only in one or maybe a few languages, and it starts working for all languages. And unlabeled data, as we discussed, like is available for a large number of languages in any case. So let me give you one concrete example of how this, I mean, some data that how well it works. So this is a particular task called XNLI, cross-lingual natural language inferencing. So natural language inferencing is you are given a hypothesis, which is a sentence, given a premise, which is a sentence, like you don't have to stay there, and a hypothesis, which is another sentence, like you can leave. You have to say whether the hypothesis follows from the premise or not. So in this case, it follows from the premise. If you say you don't have to stay there, it means you can leave. So that's an entailment. If it doesn't, then it would be either a neutral or a contradiction. So if you said you can't leave, then it would have been a contradiction. If you had said something totally different, then it would have been a neutral thing. So it's a three-way labeling or classification task. In the XNLI test bench, we have data for 15 languages, same task. And what people showed is, if you used labeled training data for each of these languages separately, then the accuracies you get are just a minute. Let me see. So let's first look at this last, cross-lingual sentence encoder, this part. So this last row shows zero shot transfer. So you only train with English and you test on all languages. Very interestingly, I mean, of course, it's not surprising that English will have very high accuracy because you have English training data. So English got 85%. But look at the other languages, right? 78, 79 and all, pretty high. If you had a random classifier, the accuracy would have been 33% because it's a three-way classification task. So it's a, I mean, tremendous gain over that random classifier. Even if you had other kinds of systems like translators, so if you had translated all the test sets to English and then run the English classifier, or translated the English training set to the other languages and tested, so this is translate test, even there the accuracies are much lower than what you are getting here. Sorry, here, sorry, in the translate test it's lower. In translate train it is a little higher, but in both the cases it is comparable. So average is 76.7 and 74.5, and we are achieving 75.1. Now why this is much better than these two? Because these two assumes that you have a translator, a good translator, but this does not assume any translator, any parallel data, nothing. So you are actually getting all these great results just from unlabeled data across languages. So people actually, I mean, like I said, there are lots of such models that are there in the market, and people have, there are competitions, there are leaderboards. So there are many such tasks, not only XNLI, but many such tasks around sentence pair classification, structure prediction, and so on. And people compete. And right now, I mean, I think, I don't know the latest result, but until few months ago, this Turing model, which Microsoft had uh, devised, you see, uh, I just want you to look at the numbers, right? So on average across languages in zero shot setup, you get 88% accuracy in many sentence pair classification task. So such a great achievement, and compare it to Embert, which was this model that I was initially talking about. So compared to Embert, it was 73.7 on average. So this is the number we are talking about. It's 75, or let's say something like 70, in the zone of 73 to 75. From there we have come such a long way. We already have like 80 on average already. So we are making tremendous progress. So this, let me know if there is any question until here. Because now we are moving to slightly different topic, which is, given that we now have the technology and you want to use it, what are the practical considerations? How are you going to evaluate, and those kind of questions. So let me know if there are any questions on the technology. Okay, if there are no questions, so let's move on to these practical concerns. The most important practical concern is evaluation. Like I told you that there is this XNLI data set. Now for this building this data set, you require labeled data across languages. Now BERT actually has this pre-trained multilingual BERT, or some of these models have 100+ languages. You want to test across these 100+ languages, then you have to go and create data set for all these 100 languages, right? So it becomes pretty difficult. So usually for language models, whether it's a good model or a bad model, how do you identify? So there are two ways. One is intrinsic and one is extrinsic evaluation. In intrinsic evaluation, what we do is we look at a pre-training objective. So the pre-training objective could be masked language model loss. So let's say MLM loss or perplexity, and try to see how that gets better over the training, or as you add more data, and so on and so forth. But this is not a great metric, because usually it does not have any bearing with the end task accuracy. Because at the end, right, what you want to optimize for is cross-lingual transfer for practical tasks that you want to solve. So MLM loss might be decreasing or perplexity might be decreasing, but that doesn't mean your accuracy over the end tasks or cross-lingual transfer accuracies would increase. Um, the other way, of course, is extrinsic evaluation, which is a, I think, better way, which is, you have a lot of task specific data and check on those tasks. The problem, of course, is you have to build data sets for each task. And one limitation is also how to compare across tasks. As we shall see in a moment, I think, yeah, uh, in a couple of slides, we will see that across tasks, sometimes different models perform better. So Embert might do better in some model and XLM Roberta might do better in some other kinds of tasks. So those issues are there, and this is just an ongoing research problem that many people are right now addressing, right? Okay, so here are some data sets that are useful if you are trying to do research in this area. XNLI has NLI dataset for 15 languages. Extreme, which came next, this is the leaderboard that I just showed you. It's from Google. It has a lot more types of data sets. So it has question answering, which is X squared, named entity recognition, and so on and so forth. It has machine translation as well, like Tatoeba, and it has very large number of languages also, between 5 and 40. XGLUE is from Microsoft. These are, by the way, all publicly available data sets. It has larger number of tasks, but fewer languages. So there are all these options that somebody can try. There are also, I mean, the Indian language representation in these, data sets are very limited. So XNLI has only 2 Indian languages, I think Urdu and Hindi, which are essentially also the same Indian language, except for the script difference. Some of the data sets like POS, tagging data set, or, Tatoeba has, or named entity recognition data sets have few more Indian languages like I think Tamil, Telugu, Marathi, and so on, but still not more than 5 or 6 Indian languages. So there are separate initiatives like AI for Bharat and all those initiatives where you have data sets specifically for Indian languages. And right now, I know that many people are working on XNLI, natural language inferencing sort of data set across a large number of Indian languages. I'm just mentioning all this because many of you might be interested in doing research on Indian languages. And I'll be happy to connect you to, I mean, towards the end, you could ask me if there are specific questions, or I could even connect you to people who are building such data sets and you could join hands. Okay, so after data set, the second set of things which are important to consider when you are training this kind of multi-LM models is, of course, the model performance depends on architecture. So how many transformer layers you have, how many attention heads you have, and so on. In general, right, bigger models are better, deeper models are better, but it's not always true, because sometimes what happens is if you have a too deep a model and very little data, it might get overfitted or it may not learn properly and things like that. So ideally, there should be a balance between how deep and how large a model you want. So training a GPT-3 for Hindi doesn't make sense because, or let's say forget Hindi, Ohmia won't make sense because in Ohmia you don't have that much data, even close to that much data as you have for English to train GPT-3. Then the other very important parameter people have been playing around with is loss function. I just talked about mass language model and translation objective. So remember the example, right? मैं प्रकृति का आनंद लेती हूँ. So and you get I love nature as the output. So this would be a translation based objective. Mass language models also we talked about, but there are also next sentence prediction, next word prediction, and many such other loss functions. And people have also tried combinations of loss functions, multiple loss functions. And if you ask, right, what's the difference between BERT and XLM Roberta, or let's say these way GPT-2 and GPT-3, other than size, these loss functions and all are some of the other differences. And the last point to always keep in mind is these models are extremely sensitive to hyperparameters. So experimentation is very, very time consuming. You have to try a lot of hyperparameters and patiently keep doing experimentation to hit a sweet spot where it works perfectly. And most researchers spend their time only with this hyperparameter tuning and experimentation. And I'm not getting into listing all the hyperparameters, right? Learning rate, number of epochs, so on and so forth. There are so many hyperparameters for these large models. Now let's ask this, I think a very important question, which is, are all languages equal when comes to cross-lingual transfer? So here the setup is as follows. You have pre-trained BERT with a bunch of languages, let's say 100 languages, and you have fine-tuned it for several tasks, but only using English. Now you are looking at the accuracy across different languages, the zero-shot accuracy. Are the accuracies similar across languages, or some language has higher accuracy and some lower? So if you remember the table before, I will quickly show you. Yeah, table here. You see the accuracies varies quite a lot. So English will be highest. Okay, 85, no surprise there. What is the next highest? I think that's here, right? French and Spanish, and also German, pretty close. So 78, close to 78% accuracy. Whereas if you look at what is the lowest, here are the three lowest languages, accuracy languages, Hindi, Swahili, and Urdu. And they have around 68% accuracy. So 10 points less than French, Spanish, and German. So the transfer doesn't happen that well for Hindi, Swahili, and Urdu. So the question is why, right? And what can we do about it? In fact, this is a graph from this paper, Extreme paper, where they show very interesting thing that, the range of accuracies vary a lot by the task also. So a task like XNLI, which I was just describing, the accuracy ranges across languages is only around 20%. So English is 85, if you remember, and the worst was also 68 or 9. So this is a small range. But if you look at something like machine translation, Tatoeba, the range is really, really high, right? From 90% to 15%. And similarly, this, right? This is part of speech tagging. So for English, it is close to 97%. But this Sino-Tibetan languages like Chinese and all, it is 25%. So this kind of raises a very interesting and important question, that while we are jumping with joy, wow, we have now solved this resource problem and we now have zero shot learning, but does it really help all languages equally? And if it is not helping all languages equally, by using this kind of technology, aren't we discriminating against languages? So for instance, if you see, Korean, Japanese are not very helped with this kind of zero shot. In fact, Indian, like Hindi, Urdu, Swahili, African languages are also not helped, whereas European languages are helped more by English. Now, I think many of you would have already guessed that English is similar to those languages, and therefore those English fine-tuning with English helps those languages. But it's not naturally always the case, right? I mean, we will see what all factors, an interesting question to ask is what all factors determine this cross-lingual transfer gap. So there are many such work which tries to do this. Here, let me try to, yeah, this table actually reports mostly cross-lingual gap for various tasks and various languages. And as you see, the highest gaps for syntactic tasks are for Japanese, dependency parsing, post tagging, NER, whereas XNLI is a semantic task where the highest gaps are for Swahili, and XQuad is question answering task where the highest gap is for Thai. So like I said, for different tasks, different models work better, different languages work better. So there is a lot of variability here. When we are saying things work, it's not, I mean, we have improved, but still there is a lot of scope for improvement. And still there is a lot of things that we don't understand. So let's try to make some guesses here. What are the things that might affect this transfer, right? So an obvious guess that many of you might have is amount of unlabeled data that you use for pre-training. So, typically the more amount of data you have in a language, it will be better. What about number of languages? If you have fewer languages as opposed to a very large number of language in the same model, which one would perform better? What do you think? During the pre-training phase, I am asking. Any guesses? Okay, I will let you think about it and we'll come back to the answer later. So what happens as we increase the number of languages in these pre-trained models, right? Then, you know, what happens to the distribution of languages? So shall we choose, languages which are in the same family or closer to each other and train models? Or should we take a diverse set of languages and then train our pre-trained, develop our pre-trained models and so on and so forth? The other thing which is very, very important is effect of script. So you see, one interesting connection between French, German, English, Spanish is not only that they are similar language, but also they use similar script, right? All of them use the Roman script. Whereas Urdu, Hindi, even though they are same language, they do not use the same script. Now that creates a big problem. See, when you are training, the algorithm only looks at the words, right? And for two words, even though they might be the same word, if they are written in different script for the model, they are different words. So it's not so easy for the model to learn that they are the same word and they should be embedded or mapped to the same point. So this is one problem. There is this other interesting issue. I mean, if you remember the BPE algorithm that we talked about, how we come up with these tokens, right? Subwords. What happens there? Uh, Higher the frequency of bigrams, higher the chance, or the string, not necessarily bigram. You will go from bigram to trigram and so on and so forth, right? So higher the frequency of a string in the corpus, higher the chance that it will be a subword. Now, what happens when you mix languages? In the pre-trained Embert model, you would have all the 100 languages and corpora for all of them. And now you are running BP algorithm and you might have said, okay, I want only 100,000 subwords and stop. What do you expect? Which subwords will be more common, right? So typically, if you have very large English corpus and very small Hindi corpus, then Hindi frequencies will never be able to compete with English frequency. So Hindi will almost always be degenerate. Each character in Hindi will be a separate word, I mean token, because that's the base you have for all languages, right? You start with the characters. But the larger and larger subwords, which are more meaningful, given that people have done what is called subsampling and oversampling and undersampling. So this is the formula using which they do it. Formula is not important, but essentially the point is, if you have low resource languages, you oversample them, and high resource languages you undersample them. Otherwise, this all these problems become very, very bad, and zero shot and all this doesn't work. But even when you undersample or oversample, still there is an interesting thing. So Roman script is used by so many languages around the world. So still you will see more frequency of Roman script patterns. Or German and English share so many words, right? And written exactly the same way. So you will have, naturally, their frequencies will grow. As opposed to Thai, which use, I mean, the only language which use the Thai script is Thai itself. So that's a big problem, big challenge, because of the BP algorithm and how we, break into subwords and all. Most other languages which don't use Roman script are actually degenerated, and you don't see good subwords for them. What else? Choice of the pivot language. Okay, so let me tell you. I mean, I didn't define what a pivot language is. So we have been talking about fine tuning, right? We have been giving English as an example of fine tuning. So you could choose any language in which you have labeled data for fine tuning. This language is typically called a pivot language. Of course, you can also fine tune with multiple pivot languages if you have data from labeled data from multiple languages. And you know, it's kind of obvious that pivots, languages which are similar, right, will help each other. So if you train with English, it will help German and French, but not probably Thai and Vietnamese. So if there are better, typological similarities between languages, typological means grammatical similarities, syntactic similarities, or there is a lot of subword overlap, like they share a lot of common words, then they will help each other more. And finally, this is a, I mean, general point. It's not language specific. In general, right, when you are fine tuning, it requires also a lot of heuristics. So often you don't, I mean, remember we said initially that you freeze the embedding and then add only a fine tuning layer and train the fine tuning layer, task specific fine tuning layer. Often that doesn't work well. What you do is you back propagate the errors from the fine tuning layer also a little bit into the embedding layers, let's say into the bird. So this is called, model reinitialization, and this kind of things actually help more. So again, getting into details of each and every one of them is difficult because they are topics in themselves, but these are things to keep in mind, that fine tuning also has its lot of tricks and tips which one need to learn so that you get the state of the art results. And finally, I want to also show you uh, a little bit about how the pivot matters. So if you're training with English, you can see that English has very high accuracy, but if you are training with French, uh, so the bold numbers in each column is for, these are the pivots and these are the targets and where you have the highest accuracy. And you can see that training with itself always gives the highest accuracy, but there are lots of interesting patterns here. In fact, if we look at Urdu, so training with Urdu gives you only 67% for Urdu, but training with Spanish gives 69% for Urdu. And in fact, actually, this should have been the bold number. I don't know why they bolded it. So there is a 70.3, which is when you train with Turkish. So interesting. So you know these are big mysteries, and people are trying to figure this out. And while I stated a lot of hypotheses, it's not always known. I mean, exactly known what are the things that help and how it exactly helps and why it helps. So we'll now move to the last part of the talk, but let me stop here for a second. And if any questions so far, I'll take them now. Any questions?
Sir, how can we apply zero-shot learning for test classification? So, Monajit sir, am I audible to you, sir? Hello. Hello, sir. Am I audible to you?
Your voice is breaking. Can you please type the question?
Sure, sir. Sure, sure.
Yeah, I will wait. Meanwhile, if anybody else have any question, I can take that as well. Okay, so the question is, how can we apply zero-shot learning for text classification? The same way, right? You have to have label data for the text classification. So text classification can be anything, right? Even analysis is a text classification problem. So the way you do sentiment, you will do it exactly the same way. You fine tune with the label data. That's it. Any other question?
Is it audible to other audience?
No, sir.
Okay. Um, Manojit, can you hear us? We are unable to hear you.
Yeah. Can you hear me now?
Yes, 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 yes.
How much? Oh, when did it got muted?
From that, from that
Because
corner,
of
from that corner, that the yeah. No, let's try to that one more.
This
Yes, 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 yes. Curse.
this.
Yes.
Oh, I see. I see. Sorry, I've been speaking through and it was on mute.
Okay.
Okay. Uh, yeah. So you couldn't hear anything about curse of multilinguality. I guess.
Yes, yes. It was mute.
Okay. Okay. I will repeat. Okay. So I had asked this question right initially, that what happens when you add more and more languages to these models. and asked you to think about it, whether the accuracy keeps increasing. And the interesting, I mean, the finding is that actually it increases to a certain extent, up to a certain extent, as you keep adding more and more languages, and then it starts decreasing, given a constant model size. So in other words, building a true universal language model would be practically impossible, because you need a very large, neural model, and you will need a lot of data to train it for a lot of languages, right? So what works the best is if you build language models for, a set of related languages. Like, let's say, I have the North Indian languages, and I build a language model only for the North Indian languages. Or I have one model for only, let's say, the Dravidian or South Indian languages. But if I start adding more and more diverse languages to it, often, it doesn't help. So zero shot works best when within a family you have a bunch of languages and you build a model dedicated to that family. So this is one particular finding. And the criticism of the current model is that they don't do it this way, right? They just take a random set of languages wherever the data is available, and they would try to build one single large model. The second criticism is, of course, it's too early to conclude, because we haven't tested our languages on our models on all languages. So the best data sets I talked about has only 40. The largest data set I talked about, NER and post tagging, has only 40 languages. But BERT has 100 languages. So what about the other 60? We have never tested them. In our own experience, right, we were testing one particular model, Turing, which is the Microsoft internal model, for a post tagging task, and we saw that Marathi accuracy was very low. And we asked them if they had any clue, and they said, no, we never tested it on anything for Marathi. Just to give an example, so you try with new languages and you will find newer things, right? So that's why one criticism is it's too early, and we should not actually say that all the current models or techniques should be replaced by this multilingual zero shot learning. Third is, we already talked about this, that all languages are not created equal in MBERT. What it means is we don't get equal accuracy of zero shot transfer across all languages. So indeed, Wu and Dresde, they say that the 30% of languages with least pre-training resources perform worse than using no pre-trained language model at all. What it means is, let's say, one of the languages with very little resource is Swahili, or let's say Marathi. Now, they will fall in the 30% of the least pre-training resource languages. Now, if you take these languages, for them, it's much better to build a rule-based system than using a pre-trained model. Because with a rule-based system, you can get much higher accuracy. Or with a little bit of label data, if you train a system from scratch, decision tree or whatever, SVMs or whatever, you will probably get better accuracy than using pre-trained language models. On the other hand, the highest resource languages like English and French, which are in the top 10%, are also hurt by massively multilingual joint training. Why? Because English has so much data that you can train very good models only just by using English data. Similarly for French, so it doesn't help them either. So it's only the languages in the middle which are kind of helped, by this zero-shot transfer. One more point is, while zero-shot is always good to have, but people have shown that if you add a little bit of, label data for a language, little bit, just maybe 10 examples, 100 examples, it takes you a long way. So instead of, let's say in XNLI, right, the table, if you remember, for Hindi, the accuracy was, or let's say Urdu accuracy was 68 or 69% when English was used as a pivot. Now, just use some Urdu label data. Let's say maybe 100 or 200 data points, then suddenly Urdu accuracy might go up by much of a margin. So this is called the few shot learning. And there was this very interesting paper recently which called which said from zero to hero, how you can very easily build these little resources and get much better accuracy. So don't stop at zero shot, basically. And of course, all these pre-trained multilingual models come up with a lot of unintended biases due to the nature of the data and the algorithms. So you might have already heard about it, right? That in word embedding models, if you ask it to complete a sentence or complete a mask, often it generates very, very obnoxious and biased content. For example, you know all terrorists are, and give it a blank, and most of these models would say Muslims. you know Nurses are typically, and it will say women. So they are very heavily biased, and this is a very big problem. And in case you are interested in choosing a very cutting edge research problem, I would suggest this fairness issues, especially in Indian language, and these multi LMs in Indian languages would be an excellent topic, because it is very little explored. And this whole notion of fairness in machine learning and AI has been built from a Western lens. Just very recently, like a month or two ago, there was a paper from Google with quite a few Indian authors who came up with this idea of, I mean, not an idea, I would say, idea has been there for around, but who very convincingly argued that why the Indian lens of fairness should be very different from that of the West. For instance, in India, caste is an important dimension where we can discuss fairness. Whereas in the West, caste is not present, so that you won't see any machine learning algorithm which tries to safeguard against caste related biases. So I think this is a fantastic research, very potent research area and very important research area going forward. And if I mean, this is something which only Indians can do, because the India is such an interesting, I mean, not only linguistically diverse but culturally also so much diverse, that these fairness issues are also very different from most of the Western world. So yeah, the criticism here is these models are biased, and we somehow need to debias them before we start using them. Let me don't get into the details of it here, but I mean, if you are interested, I'll be more than happy to answer more question or engage in discussion after the lecture. So from criticism, let's move to this last point about BERT before we get into the Indian language NLP context, uh, which is BERTology. Now, how does it really work? And unfortunately, the short answer is we don't know. But there are all sorts of interesting hypotheses, and the space is again evolving pretty fast. So let me tell you a couple of hypotheses. First hypothesis that came up when Google did their original 2016 paper was, Google said that probably this multilingual space is learning something called the universal grammar. So many of you might already be aware, right? Chomsky had this notion of universal grammar, which says all languages essentially has the same grammar, but it's only certain parameters within the grammar that varies, and this variation gives rise to a large number of different kinds of languages. So Google's paper, in the paper, they hypothesized, okay, maybe we are seeing this universal grammar being learned by these networks. It was in fashion for a while, but people did not buy a lot into the argument. First of all, not everybody even agrees that there is a universal grammar. And even if you agree, there is no solid evidence that the machine is learning some universal grammar. A more plausible thing is shared vocabulary. So what happens in shared vocabularies, like we already said, right? English and German has a lot of shared words. Similarly, English and French has a lot of shared words. And these shared words have similar meaning or same meaning often. So these actually are the cues that the machine is using to map the embeddings into the same space. Okay, great. Works for English, French, German and all. But what about, let's say, Hindi? because in Mbert, Hindi and Marathi are the only languages which use the Devanagari script. How on earth you would map that Devanagari token or Devanagari script words to the same space as Roman script, Arabic script, and all other things. And similarly, you could say the same thing for Japanese. Japanese is the only language which uses the Japanese script, or Chinese, and so on and so forth. So to which people came up with an ingenious argument. They said, well, it's trained on Wikipedia, and Wikipedia have numbers. Wikipedia has, some English words like, IPA pronunciations. If you open any Wikipedia page of Hindi, you will see a lot of, pronunciation, how to pronounce the word, which is written in IPA, or a lot of numbers which are in Roman script and Arabic numerals, basically. So probably these are the cues that BERT is using to map them into the same space. So this is the shared vocabulary hypothesis. So interestingly, there was this paper again in 2020 where they showed that shared vocabulary isn't necessary. So what they did is very interesting. They took English and Spanish and mapped them into the same space. Now English and Spanish shares vocabulary, so naturally it's not surprising that the cross-lingual transfer works there. They learn a shared representation. Now what you do is take the English corpus and offset each character by a fixed number, so that the entire letters, all the English characters, go to a space, Unicode space, where there is no character overlap with any language. So they call this fake English. Now they take fake English and then they take Spanish and learn embeddings, and with that they do zero-shot transfer, and zero-shot transfer works there too. Maybe a little less accurately, but the loss is not much. So it shows that shared vocabulary is not necessary. It helps, but it is not necessary to learn a shared representation. Then there is one more interesting line of investigation within Bertology. So many people have been trying to argue that each layer. So remember, there are these encoder layers, and BERT large has these 12 encoding layers. So people are saying after each layer, the encoders actually are processing more and more deeper syntax going towards semantics. First layer is maybe morphology, second layer is maybe pause tagging, third layer maybe, so almost like the classical NLP pipeline. Pause tagging, and then it might be learning, gram dependency or some kind of parsing, semantic roles, and so on. And people have showed this through probing experiment that to some extent it is indeed the case. But then people have also shown that while some layers might seem like giving a lot of information in the encoding to do pause tagging or do syntactic processing and so on, it's not necessary in the sense that if you actually take that layer out, even then you can do pause tagging. If you take a layer of semantics out, even then you can do natural language inferencing. So in some sense, the representation is pretty distributed also. It's not, a linear pipeline. So I'm very sorry if I'm totally confusing you here, because we all are confused. Actually, it can't be helped. We all are confused. It's like fascinating, and we all are trying to figure out what happens. And somebody finds some cue and writes a paper. After a month, somebody else say, okay, no, this is not always the case. I can tell you also briefly what we are working on right now in this space. So we are looking at when you are training with code mix sentences, what happens to BERT? How the attention patterns change. And what we have observed at a high level is if you only have English and Hindi pre-trained model, jointly pre-trained model like MBERT, so then, when it sees a code mix sentence, there are certain neurons or certain attention heads which gets fired. So the information is not distributed. It is like, concentrated. Whereas if you actually pre-train it with code mix data, then suddenly the information gets distributed. Now, what's the benefit of information getting distributed? Then the model becomes more robust actually. So a lot of heads are now paying attention to code mixing. So again, this is just an observation, and whether getting distributed attention is useful or not. I mean, useful is also an observation, but why it is useful is something which is just our guess. So we don't know. But what we observe is when you pre-train with code mix data, the attention gets distributed. And when the attention gets distributed, you get better performance on code mix tasks. This we already talked about, like what kind of effectiveness, and I will skip the typology bit for now. We can come back later if you have questions here. So in one sentence, the languages of the world in terms of their grammar and other kind of linguistic properties vary a lot, and this is quantified by linguists through this entire field called language typology. I mean, this is described, not quantified. This is described using language typology and typological features. And people have been studying a lot of, with lot of depth, how much typological features affect cross-lingual transfer and those kind of things. Like two languages sharing word order might act as a better pivot for one another. Like both French and English and Spanish are subject verb object, right? Word order. So they might actually help each other in zero shot transfer, whereas Hindi is subject object verb, so English doesn't help Hindi. So this kind of things. So any question before we move to the last part, which is the Indic context? Okay. If not, so let's get into what repercussions does all these have on Indian language NLP. So I already showed you this graph. I explained you. I won't get into the details again, but I will just show you two things. So one is, you see, in the fifth class, which has all the resources, languages with all the resources, which is this class 5, there are only 7 languages, English, Spanish, German, and so on, 2.5 billion speakers, but only 7 languages. That's 0.28% of the world's languages. In class 0, on the other hand, there are 88% of the world's languages and 1.2 billion speakers. Now, if you look at the graph carefully again, you will see that these languages fall in the top 10%. And I already discussed that they are not benefited by pre-trained language modeling, because multilingual pre-trained models, because they already have enough data to train models, monolingual models. And these, right, class 0 and class 1 and class 2 languages are also not helped, because these are languages where you have so little unlabeled data that you cannot do much. And even if you have labeled data for some of these languages, you have no data to test, at least no labeled data to test, much enough labeled data to test. So 0, 1, 2, 3 is also not benefiting. So it's actually 3 and 4 which are getting benefited, and mostly 3, because 3 doesn't have labeled data, but they also have enough unlabeled data to get benefit of this. So that's why in our paper we call 3 as the rising stars. And Tamil and Marathi are the 2 Indian languages which fall in class 3. Bengali and Hindi are the only 2 Indian languages which fall in class 4. Everything else is in 2, 1, and 0. So 2 has a language like Konkani, and Assamese and Bhojpuri are in 1. And Santhali, which is also a scheduled, one of the 22 scheduled Indian languages, fall in class 0. So you see, most of the Indian languages are not even have much of a hope from all this, unfortunately. So only 3 and 4, so which would be Bengali, Hindi, Tamil, Marathi, and maybe Telugu and few more languages. I can think of 3, 4 more languages which might get all the benefit, a good amount of benefits. Everything else, like Gondi, Mundari, Santhali, Bhojpuri, Assamese, I don't think will get much of a benefit of all this. So what should we do? So languages which get some benefit potentially, like Hindi, Bengali, Marathi, Tamil, Urdu, for them, the thing we should do probably is to build more and more evaluation data sets. And once we start doing that, we will probably, be able to see where the gaps are and push in more resources. I mean, research there and work there and so on. Fortunately, there have been quite a few good initiatives. People have been creating Indian language data, but they are not available in the same place. So this AI for Bharat initiative has put all these data in a single place. So it's a very large catalog of Indian language data, and they have also released their own data sets. So if you are working on Indian language space, you should definitely go and visit this and see what all things are there which help you and how you can contribute. If you have data sets that you have created, you can contribute actually. Your data remains your data. It's just cataloged there. Glucose is another data, initiative from our lab. So glucose stands for glue for code switching. Code switching and code mixing are the same thing, more or less. So glue is, remember, that generalized language understanding evaluation. So this is an evaluation for code switching tasks. So we do have one English Indian language, which is English Hindi. So a bunch of data sets like part of speech tagging, natural language inferencing, and so on and so forth for this. Most of these data sets are collected from other sources. We have put them together as a benchmark. This natural language inferencing data set for English in the code switch text was created in-house. These are just some numbers which shows how good performance we have with pre-training with code switch data over BERT. I think it will be really important here. It will be a little bit of a digression, but let me just tell you that one of the very important thing in Indian language context is also code switching. So if you are, Indians hardly ever speak the same, one language. Most people would mix languages. And when you are mixing languages, then tackling code switching becomes important. And a lot of these models like MBERT and all are not trained on code switching, so that they don't naturally work on code switched data. And this is what these actually numbers show. So what it shows is, this is the pre-BERT SOTA, right, for various tasks. And with MBERT, you get a much better, improvements. Let's say for pause tagging, you get from 77, it goes to 87 in one of the data sets. In all data sets and all tasks, it improves. However, you can further improve it if you actually do what is called continued pre-training with code switched data on MBERT. So you take the off-the-shelf MBERT, take a bit of code mixed data, and further fine-tune, further pre-train, sorry, not fine-tune, further pre-train the MBERT model, and then now you fine-tune for task. And once you fine tune for task, you see that you get some further improvement. This is not very consistent across all tasks for English Hindi, but you do get, for some tasks like pause tagging and language identification and natural language inferencing, you get some good amount of benefit. For English Spanish, it's more systematic. You get benefit on all tasks actually. Yeah. So yeah, let me actually stop here, and I will just summarize, and then we'll have a plenty of time, maybe half an hour, to to answer your questions. I wanted to leave it that way because I think you might have a lot of different questions depending on what kind of research you are involved with or problems you are dealing with, and I would be more than happy to answer those questions. Yeah. So a quick summary. We saw that these massively multilingual LMs have revolutionized NLP because there is no need for label data across all languages. But then, what language you are talking about, how much data we have for pre-training, what is the pivot language, hyperparameters, all these are very important factors in performance. So it just is not, even though it's magical, but at the same time, it isn't magical. There are lots of nuances and tricks that one need to know. Not all languages are benefited equally. and not all languages even have enough unlabeled data to train good models. For Indic languages, we need to create data, especially evaluation data, because even if unlabeled data is available for 6-7 Indian languages, but evaluation data is not available even for them. And if you want to go to the tail, then the story becomes completely different. These models may not be even appropriate for the tail languages where there is no data. And finally, multi-LMs, as I said, it's a very ongoing hot research topic right now, very actively pursued. And if you want to work on it, then I think this is one of the great topics, especially in the Indic NLP context. Let me stop here. Thank you. And let me take questions, comments, anything.
Sakshi?
Yes, sir. So the participants, anyone who wants to ask questions can go ahead. Or just post the questions in the comment section. I'll read that.
Hello, sir. First of all, thank you for this wonderful
Yes.
talk. I want to ask with respect to code switching. So in code switching is the mix-up of two different scripts involved, or in a single script, two different languages are involved?
This is a very good question, actually. It can happen in multiple ways. So in case the languages use the same script, right? Like Spanish and English, usually people will always code switch using the same script, Roman script. However, in Indian languages, and when you are code switching language, let's say English, since the scripts are different, what happens is often you will see that the entire thing might be typed in Roman script, like in social media. So people will even type Hindi using Roman script, and the English words are also in Roman script. Sometimes people will type the entire thing in Devanagari, though that's very less common. Uh, so I would say 70% of the time people use all Roman script. 15% of the time people use only Devanagari script in social media I'm talking of, and 15% of the time people use mixed script. So mixed script is when you type the English words in English script and Hindi words in Devanagari script. And that's also not, I mean, that's only common in media houses. So officially when people are typing something, they will try to do that. But most of the people, when unofficially, talking to each other informally, they usually don't switch scripts, because switching script is technically or interface wise a little complex. Does that answer your question?
Yeah, yeah. Thank you, sir. And one more thing, sir. Suppose if the training is been done in a joint fashion, then I guess let's
Mhm.
suppose we have some diverse language pairs involved. And with this regard, how is the parameter sharing done? Like, is complete parameter sharing is good, or some kind of like sort of partial parameter sharing or something like that?
So usually it's a complete parameter sharing. So in MBERT like models, right, there is no partial parameter sharing. So the models, I mean, only the word to vec models are separate, the initial embeddings, but after that, all the encoders and everything are same for all the languages. Now, once you have complete parameter sharing, I mean, you have very little control about what the models learn. Now, one way to ask, I mean, and probably what you mean when you ask this question is, if we were to build a model where I just shared some layers and not all layers, right, for languages, then what happens? People have tried such experiments. There are sometimes some benefits, but it is not consistent, because you get a lot more, I would say, uh, the space that you explore becomes a lot larger. You have to explore. So how many layers to share, how many layers not to share, whether you share the top layers or the the lower layers or the deeper layers, and so on and so forth, right? So you would try and play around and you get some benefit, sometimes marginally, but I haven't seen much work about partial parameter sharing across languages.
Okay, thank you, sir.
Sir, one participant wants to ask a question, Amit Trivedi. So,
Right, I
he wants
saw.
to ask, what are the open areas in NLP to work on?
Yeah, yeah. So this is a very open question, open-ended question. I don't know how best to answer, right? I will put it in this way. So there are theoretical questions, and there are applied questions, and there are, you know, uh, how do I put it? Like uh, user-centric questions. Uh, Theoretical questions are obviously, I mean, easy to understand, right? All the questions of Bertology, how BERT works, and all these will be theoretical questions. Or even building some of these models might be, broadly theoretical. Applied is once you take all these things that people have already built, let's say BERT or any other algorithm, and now you are trying to use it to solve a particular problem in a particular language. So that would be applied. And the last bit, which I, in need for a better word, I said user-centric, is more like when you really want a group of language users to benefit from the technology. You really don't care how the technology is to be built, but what you care is what technology should I build so that this group of users benefit from language technology. So there it is more like NLP for social good, and you are deploying the technology. It need not be always social good, it could be a business good also, right? I mean, you are trying to build a startup based on an NLP technique. So you really don't care what technique to use. You are not comparing between techniques and so on. You want something that works, and that will bring you business. Now, if you look at all these three pillars, there are different sorts of questions there. I think most of the open questions are in the last pillar, because NLP has been, mostly restricted to research papers until, let's say 10-15 years ago, when it suddenly started becoming very popular in industry. And now NLP is very, very popular in industry. So the second pillar is also covered there. The third pillar, taking NLP to real people, especially across a large number of languages and all, hasn't been done that well. So I think there is a lot of research scope there. In the first pillar, I already mentioned the research. Some of the interesting questions are explanation, so-called FATE, fairness, accountability, transparency, and explainability. So these are the four important questions that everybody is struggling with, and how can you make NLP techniques more fair, more explainable, and so on and so forth. Then, of course, how BERT works, how these systems work, what linguistic repercussions they have, and so on. The middle pillar, the applied pillar, where you are building something for a specific language, I think for Indian languages, there is a lot of scope there too. Because I said, like, there are languages, a lot of languages missing data sets, a lot of languages missing even basic tools, techniques, and all that. So, I think there are lots and lots of scope, and depending on what interests you, you can pick and choose. Does that answer your question?
Yes, sir. He's saying thank you, sir.
Yeah, I saw that. Okay.
So anyone else who wants to ask
Since nobody is
questions?
asking,
Hi, sir. Hello, sir.
yes, please go ahead.
Sir, is it possible to work zero-shot learning along with any pre-trained model? So, I mean, is it possible to develop any hybrid model?
hybrid model. So definitely possible. I have seen people mixing, embeddings with word to vec. So suppose you are building a model for Hindi, you are directly using Hindi word to vec embedding, plus also, embed models, plus also some other SVMs, and then do a voting after that. So people have done all sorts of things, mix and matches and all. I find most of those very ad hoc, and very, I mean, there are no principles, so to say, on how best to do that. Voting, of course, is a very standard thing in machine learning. So you have a bunch of classifiers and you are getting output of all of them, and there is a mechanism through which you choose one final output. So there are principled approaches to voting, and you don't really care how these classifiers individually work. However, I think more interesting question to ask would be how these various kinds of models like word2vec and BERT and embed can inform each other and learn from each other, right? And I really don't know. Uh, I I haven't seen much work in that direction.
So what kind of word embedding model is going to be give best accuracy while working with the pre-trained models?
Uh, it's not about what kind of word embedding models, in the sense that you know you have to tell me a lot more. Tell me what language you are interested in, what task. Then go and look at papers, what people have worked, and people would have reported like this works best for this task. Then choose that. If people haven't, I mean, people may not have reported for your language, then you try multiple things and see which one works best. So it's all experimental. It's very difficult to answer. There is no single answer.
Okay, okay,
You have to experiment basically.
okay, sir. Thank you, sir. Thank you very
But
much.
there are general rules of thumb. Like one transformer based models like BERT and Roberta works better than Word2Vec kind of models. And even within BERT and Roberta, if you can have access to a large domain specific and language specific model, it will typically give you better accuracy than a generic mbert kind of a thing, unless you are interested in a cross-lingual transfer, right? Suppose you are only interested in Hindi part of speech tagging. So since there is Hindi label data for part of speech, instead of using mbert, you might want to use, Mural, which is the Indian language specific language models. For instance, I mean, I'm just giving an example.
Sir, may I know any practical references for zero-shot learning?
I will share the slides. There are many, many. Yeah. So
Okay,
in
sir.
the slides, I have many references.
Okay, sir. Thank you, sir. Thank you so much for answering my
Yeah.
questions.
And there are very, very nice. Yeah. There are very nice blogs. I think I have references to those as well. Or I will add them before sharing. So these blogs actually, yeah, I do have actually references to the blogs. So these blogs explain zero shot learning and all these, large transformer based models very neatly using visualization, animation and all. So they're very useful.
Thank you, sir.
Okay. Any other question?
Participants, anyone who else wants to ask question? Okay, sir. Then I think there are no more questions. Yeah, thank you so much, sir. It was really a wonderful and amazing session with you.
Thank you, Sakshi,
Thank you so much.
and thank you everybody.
Okay, so we thank the speaker and we thank the participants for the first part of this session today, and for the second part, we will assemble at. We'll be joining the meeting at 3:30. Thank you, Manojit.
Thank you. Okay, bye bye.
Bye.